Okay, today's chapter on differential protection. Now, differential protection is very important principle of protection uh, in power system protection. Uh, it can be used for different, to protect different types of equipments. Okay. And now, what's the problem? Why do we need this, and how it operates? Okay. So why do we need differential protection? Its application. Where do we apply it? And what are the difficulties when you apply this type of protections? How do we solve these difficulties? I'll give you a design examples. Okay. So in overcurrent relays principles, if I have a relay here at the beginning of the line, and we know that its operating time depends on the current magnitude, it's inversely proportional, right? As current increases, the times decreases. Now, this is now if I use IDMT characteristics. Okay, standard inverse, very inverse, all they operate in this inverse relationships. Now, that makes the relay, okay, its time varies as type of faults change. You know, if the fault at the same location, because suppose the fault at the middle of the line, for line to ground fault, I will have different current. For line to line fault, I have different fault current. For three-phase faults, I have another fault current. For three-phase, I have higher current than line to line, or higher than. So that's mean, although fault is same location, but because fault is at different at different value, I will end up with different operating time, although fault at the same location. So it doesn't give me a specific, a fixed operating time. Okay, so I want, this is one issue with overcurrent. Second, if the source impedance changes, and source impedance changes as you know, the generator, when you increase the number of generators to the systems, the source impedance decreases and fault current becomes higher. You know, the I fault depends on the fault impedance, is the voltage at the source divided by Z fault. And Z fault, let's say, is the impedance from here to the fault point. So as Z source changes, if this decreases, I fault will increases, even if the fault at the same location, and because of this source changes. As a result, also, the operating time will, even for the same three-phase fault at the same location, when the Z source changes, the operating time changes. So this is one problem of overcurrent relay, that time is not fixed, is varying as system changes, system parameter changes, or fault location type changes. Now, the second problem with overcurrent relay is the complexity of setting. You know, you need coordination from one relay to another. I have difficulty with when I have ring systems or loop system. You know, you cannot apply non-directional relay. It has to be directional relays. And as a result, to overcome this problem, to get a relay that always instantaneous action, okay, fixed time, and it's not affected by type of faults or system source impedance variation. That is over, you know, this type of protection that provide this feature is the differential overcurrent principles. Okay, so the advantage of this is to provide instantaneous actions. Okay, fast action. It is selective. Selective means selectivity means if I have a line and you provide differential relay, differential requires, you know, it takes the difference between two currents. Okay, so this is the differential relay. Uh, its zone of protection is defined by the two CTs that's connected to that differential relay. Any fault between these two CT, this differential relay declare that this is a fault, internal fault. Any fault outside the two CTs region, they will declare this is as outside. So that's why we call it unit protection. Unit is the unit between or the equipment or unit that is connected between the two CTs are, or the protected portion. So it has very fixed or cleared zone of protection. It's very sensitive, it's, an overcurrent relay, we choose the pickup settings higher than full load, right? So the current has to be greater than full load for the relay to operate, while in differential, the setting can be set at even 20% of full load. For generator, we can go to 5 to 10% of full load. Okay, so it's very sensitive pickup settings. However, it has also drawbacks. I will highlight it later. It of course is higher cost as compared to overcurrent. It doesn't provide a backup, okay, to other protection system. It's just protecting one equipment. It doesn't provide a backup for others. Applications can be applied for different types of equipment. I can use it to protect a transformer windings. I can use it to protect a generator winding or motor windings. I can use it to protect bus bars. I can use it to protect a feeder or transmission line. I can use it to protect shunt reactor or shunt capacitors. Okay, so there are so many applications. For differential protections. The working principle is very simple. It's based on KCL. Okay, differential relay is based on KCL. So if I have this is protected equipment, could be a transformer, a generator winding, could be a bus bar, it could be a transmission line. Okay, so suppose if this is a transmission line, the current entering a transmission line should equal current leaving the transmission line. If I put a CT at the beginning and the end, and I take the difference between them, so this is I1, okay, and this is I2. So this is also I1 over the CT ratio 1, and I2 over CT1, and this is I2, we'll call this I1 prime, I2 prime. Okay. Now at normal operating conditions, if this is transmission line, current inputs equal to current output. Okay, ideally. And so this current and this current, if I choose same ratio, this current also will be same as this current. If I take the difference is 0. And if difference 0 means there is no fault between the two CTs, so the breaker, there will be no trip action. If these currents are different as a result of a fault somewhere here, this current will be, I1 will be I2 plus I fault. Okay, so I1 and I2 will be different, and we take the difference between them will be I fault, and because they have difference in current, the relay will send a trip signal for the two circuit breaker at the two sides of the protected equipment to trip. Okay, so in this case, it's KCL principle. I just add or subtract currents to check if the difference is 0 or higher than 0 or 0. It could be as a bus bar. So bus bar, suppose I have 3 circuits out leaving the bus bar. This is the feeders leaving, and I have 1 input. Okay. This is now if I put a CT here, a CT here, and a CT in each portion. So I'll call this, let's say, I1, I2, I3, and I4. and these are in this direction in normal operating conditions. This is load side. Load side, this is the source side. Now, by KCL, during normal operating condition, I1 at normal, we have operating condition that I1 should equal minus, or I1 minus KCL, minus I2, minus I3, minus I4, okay, should equal to 0. If this is not equal 0, if this is the difference, so this is the differential. If the difference greater than 0, this means there is a fault. So during fault condition, so this is called I differential. Okay, so during fault, not fault, internal fault. Fault could be external. If the fault somewhere outside, I'll say fault outside. Suppose it's fault external. I'll say it's internal here. F1 in the bus bar. For fault at F1, what would happen now? I1 should equal to, this is, I'll call this I fault. Okay, that goes to the fault. So I1 now, if you subtract I1 minus I2 minus I3 minus I4, I differential will be what in this case? Equal to I fault. Because I1 plus I fault plus I2 plus I3 plus I equal to 0 now, KCL. So if you take now this, okay, minus also I4 equals 0, so ID, which is this, programmed in the relay, is I1 minus I2, I1 minus I2 minus I3 minus I4, which is I differential. It will be now in this case, during fault, I fault, which is greater than 0, so relay trips. Okay, it declares internal faults. For fault now, external fault somewhere outside, I will say now fault here, fault F2. So external fault, outside, F2. Now if you take F2 now, this is I4, the same as I2. I2, this is I2. Okay, so in this case, I differential, which is I1 minus I2 minus I3, still equals to 0. So relay will not trip, no trip. Action. So based on just this equation, if I implement this inside the relay and see it if it is greater or 0, trip. If it's not equal, greater than 0, the magnitude of this. Okay, all time looking for the magnitude of the differential equation. Okay, this is the working principle, as simple as this. Now we have some equipment that has 2 terminals. In this case, I have how many? 1, 2, 3 terminals, and each terminal is represent 3 phases also. So this, I'm comparing phase A with phase A with phase A with phase A, KCL. Phase B with all phase B units, and so forth. Okay. Now in this case, if I have a relay protecting a differential relay, now it's a principle here, something like this. Now suppose this is a line also, okay, and I have a current flows in the primary side. At the sending end side is I1, at the receive side. So here, the current here at the secondary will be I2, okay, over CT ratio 2, sorry. And this current will be, like, suppose this is the polarity marking, current input here should correspond current output here. So this current will be, which is this, hey, this will be I1 over CT ratio 1. And this is I2, current leaving a dot, correspond current entering a dot, polarity marking here. So this current will be in this direction, and this current will be in this direction. So it will be here, and will be here. So what is this current now? What is this current? And this current, now this is, or this current. So let's call it in down. We'll call this, suppose here an overcurrent relay I bought. So this is called the differential relay, ID, which is equal to I1 minus I2. Of course, I1 over CT ratio 1, okay, minus I2 over CT ratio 2. If I choose now, on this case scenario, if this is transmission line, I'll choose CT1 same as CT2, okay? So in this case, okay, in this case, I1 minus I2 give times 1 over CT ratio, because they are same. So if these are equal, I end up with differential is 0, okay? When these two currents are not equal, because of internal faults, the differential will not be equal. So this is called the differential current that will flow an overcurrent relay. So differential relay is an overcurrent relay, but the current through that invariant current is not the line current or phase current. It's the difference between currents. Now for external faults, as I mentioned, these two currents, okay, these two currents are still same for external faults. This current and that current are still same, so the differential current is 0. Differential current also sometimes is called spill current. When internal faults happens, for internal faults, this differential, the I1 will equal to I fault plus I2, and as a result, these two is not equal to 0. Okay. There are some situations where it makes these differential relays not exactly 0. Suppose I have problem, the CTs are not identical. Yani, although the primary I1 equal to I2 plus I3 plus I4, but the secondary, due to the magnetizing current, IE, are not equal, you end up with I secondary might not be equal. So this is one issue you have to, I might have a false, I would say, differentials due to some problems. One of them is the CT magnetizing characteristic are not identical. One of them is the CT ratio is not the same. The ratio at the different places are not identical. I'll show you examples, inshallah. Saturation of one CT could lead to also a differential between relays. In rush, we have a transformer, and during starting you have primary current, but you don't have secondary current. This relay will see it as a fault, but this is just a normal operating condition of switching a transformer. When you have vector groups, some transformer, this delta star connection, the primary is not in phase with the secondary currents. So that will lead also a difference in current due to the currents are not in phase. And if you have also a tape changer, you have to consider that into consideration if you have a transformer with a tape changers. Let's show you one issue here. Suppose I have two CTs. Now I am trying to compare two. So I have one CT here, another CT at the end of the line. Okay, and these two CT1 and CT2 are not, they have these characteristics, and I want to compare them. Okay, these two characteristics of identical. What happens is now this CT output here, I have one branch magnetizing current here, right? This is IE1, and the secondary here also current IE2. So the primary current is, although it is I1 during normal operating, same as I2, okay, but this current I secondary 2 is not equal to I secondary 1 because of this IE1, not same as when you have CT characteristics are different. So so suppose now this voltage and this goes to the relay. And this is the relay. So the relay now I'm assuming the relay at the center between the two. So the burden seen by this CT, which is the lead resistance plus this relay resistance. So because of this, so I'll have if the suppose if the characteristics are different, and this is the voltage Vs for the two, this will see this current IE, and this will see this is I2. When this IE1 and IE2 are different, I secondary 1, which is this current, this is IS1 prime. IS1 prime minus IE1 gives you IS1 current. And similarly here, I have IS2, which is IS2 prime minus IE2. Now, if IE1 and IE2 are different, there will be a different differential current equivalent to IE1 and IE2. And as a result, if I this will create an error, a differential current due to the two CTs are not having same magnetizing characteristics. So I can overcome this by not taking a differential current just greater than 0, but I make it greater than certain threshold to overcome this error. This second is saturation. One CT saturate, suppose now these are the current for external fault here, high current. Suppose one of them gets saturated, second is normal, not saturating CT. For a saturated CD is the solid line. For non-saturated CD is the dotted line. And if you take a difference between them, now you'll see a signal. Now here, if I try to draw the differential current, you will see differential current here 0, 0, 0, because the dotted line and solid line are together. At this point, they will split. So if you take the difference between this and this value, okay, I'll have positive. So this high will be maximum here. Then at here, there will be also 0 again. So it will be a differential current, then 0. Here also another differential current will become 0 at this moment. Okay, and here 0, then I have differential current. Then I have a differential current. So differential current will looks like this. So this is the I differential. If I'm using, and because of this, the relay might trip because there is a differential current. It's not because I have a fault inside between the two CTs. That's because one of the CT gets saturated. Now, how do you overcome this problem? And sometimes we have also, in case of transmission line, you know, you talk on power system 1, transmission line, primary currents is not equal because of have shunt capacitances, no, in transmission line. And because of this, the received end I2 and the sending end current I1 at normal operating conditions is not same. So if you take difference between them, it will give you a differential current even during normal operating conditions. So the settings of the relay should be greater than this normal differential current that goes in the capacitors. So when you take I1 minus I2, in this case, give you the capacitor currents. So what are the solution? We have two solutions to these issues. One of them we called it, we use a high impedance differential protection by adding a stabilizing resistance. Okay. The second is the bias differential, bias differential protection. Okay, and that's by adding, by increasing the setting as the current magnitudes increases. So I'll just show the two solutions today, inshallah. Later, inshallah, I'll show you examples. Okay. In the first high impedance differential, we can add in series with the relay, with the differential relay coil, resistance in series with it. And this resistance, large resistance. I'll show how do we choose this resistance. Now, the idea of this resistance, that if one of the CT gets saturated, I don't want this relay to operate. Okay, this is the purpose of this. It will stabilize relay, not operate if one of the two CT gets saturated. Now, this is the worst case scenario that affects the CT, the differential relay operation, accuracy or the selectivity of differential relays. Now, the working principles. Now, this is the protected zone. This is CT1 and CT2. So on this scenario, this is our assumption. I will assume there is a fault current just after one of the CTs, and that cause one CT is fully saturated. So when it's fully saturated, this becomes short circuit almost. That's a representation of CT saturation. And now this, I will assume also the magnetizing branch of this is infinity. Okay, this is not saturating at all. So the current here, okay, and current here is same. So in this case, during this scenario, so I'm assuming direction in this way. Under this scenario, and the relay, this is the relay, differential relay. Suppose it has a resistance R. This is the relay resistance, okay? Relay burden. And this is the resistance I want to add in series with the relay, okay? And relay has a setting. This is the pickup setting of the relay, IS. The settings of the differential relay that pass in this relay higher than this settings, relay will declare this is a fault, okay? Now I have to find, I don't want the relay to operate during this scenario, okay? Because this is external fault that leads to one of these to saturate. I don't want this to relay, I don't want this relay to operate. Now, during short circuit of one of the CTs, this is the CT secondary resistance for 1, and this is for 2, and this is the lead resistance. Normally, if one CT saturated, the resistance of the lead plus CT is much smaller. I want to choose this resistance much larger than this resistance. When you choose this, then the current that will flow here will not go here. It will go to this, like this branch will be parallel with this branch. So the always current flow and the least resistance branch. So I'll choose a resistance R as very large compared to the lead resistance and CT resistance. Okay. And as a result, now this current will be almost same as this. As a result, I'll be able to find the voltage between these 2 points. So what is the voltage VR? Is the voltage between this point to this point as equal to roughly this current times the some resistance of this R3 and RCT plus RL. So VR is equal to the fault current. Now this is the fault current. Refer to the secondary side, right? This current refer to secondary side. This is I fault. And the I fault you multiply, this is also I fault. This is approximately I fault, okay, times the resistance of this RCT plus 2RL. I'm assuming this is RL, also this is RL, gives you the voltage across these two terminals. Now, if you divide this voltage, okay, if I divide now, what is I differential? What is this current I differential? So I differential, whether it's in this direction or this direction, doesn't matter, you see. I differential is equal to VR divided by the resistances of these two, which is R saturation, that I stabilizing resistance, plus resistance of the relay. Okay. Now, what I don't want the relay to operate under these conditions. I want the differential current now that will flow, this differential current, or in the other direction, doesn't matter, is less than IS, than sitting current. So I want this to be less than I sitting for the relay not to operate. Now, how do I make so? I want to choose now IS. So if I solve for IS, this equation, it will be like RS stabilizing plus RR should be greater than, right? If I go here, it will be greater than VR over IS sitting. And now R stabilizing has to be equal to greater than VR over IS minus RR. So I have to choose a stabilizing resistance that's greater than VR, and I know what's VR, okay? I know the maximum fault that occurs here, I know from, right? I know RCT, I know, so I know VR. So, and I know the pickup settings of this. So I can choose, as I told you, we choose a pickup setting 20% of my secondary rated current. So I know the I settings, I can choose a stabilizer. Now, how much higher? They said, okay, you can choose 1.5 higher, up to 1.55. It could be 1.2, 1.3, 1.4, up to 1.5. So I can say this is equal to a K factor times VR over IS minus RR, where K is a factor greater than 1, which makes now this higher than this. Okay. So this is the principle of the high impedance differential protections. The second solution is called biased differential. To know what's biased, I will just show you what's unbiased differential. Now, normally, as I mentioned before, the differential current could be not equal zero even during normal operating conditions. If I have one of them is when these two CTs are not having same magnetizing characteristics. So I have a differential current. So as the current increasing in the primary, the difference also increases. So this is called an error, the relation between I differential and I primary current. So this is I primary current with differential current. So I primary, or the average of I1 and I2 on the primary side, okay, we call it as this increases, the difference increases, error difference, due to when the two CT are not matched together, not exactly matched. This is called CT mismatch, CT ratio mismatch. We have other error due to the magnetizing characteristics. When the magnetizing characteristics of these C2 are not matched, so you have this green area error. When you have a transformer with a tape changer, also will create an error. This is the blue area. And also if you add another factor, safety factor, so this is the error curve. As the current increases, the error between these two currents increases. So I should have a setting that should be higher than this error for the relay not to operate during normal operating conditions or during external faults. And now suppose at maximum fault external, this is I fault external, this is my fault external, and this is the maximum error somewhere here. So I have to choose, for unbiased, I have to choose a setting for the relay higher than this error. So if the current and a differential current exceed this settings, the relay operate. This is operation. When ID greater than I settings, the relay operate. If the current less than I settings, relay restrains. Okay, so the red area here, operation region, the white area is non-operating region. However, that will lead to high settings. This we call this is insensitive enough. To make it sensitive, it's better to get a setting which is goes parallel with the error. Okay, so that so on this, how do we do this? You know, this is solved by using bias differential. That the settings, as current increases, the settings start from low and it increases as error increases. So how do you achieve this? By using a bias coils in electromechanical relay. Now these are not coils, okay? Now these are just something proportional, these two currents, okay? So this is we call the operating coil in electromechanical principle. These are the bias coils. So in numerical relays, as you know, we have two quantities that you want to compare: the x-axis quantity and the y-axis quantity. The y-axis is the differential current, is I1 minus I2. Okay, the magnitude of this. Okay, so this I differential is I1 minus I2 minus I2 magnitude, the difference between them. And the second quantity, we call it the restraint signal or bias current signal. And you take the average of these two currents. So this is equal to I1 plus I2, but the magnitude of both, magnitude of the first one plus magnitude of the second one, okay? divided by 2. So that gives you the, we call it the restraint quantity. And now the settings is somewhere change as this current change. This is now the curve that represents the error. As current increases, error increases. Now I want the relay pickup settings higher than this error. So I will start with the low value, okay, settings, and then increases, okay. So how do I achieve this trip conditions? Suppose now, now this is like made of two curves. The first curve is the straight line, which is this. Okay. Now when the current, when differential current higher than this settings, means I am operating here above this green line. This is condition number 1, and it has to satisfy also condition 2. Condition 2, I'll draw it with the blue line. Which is this straight line equation. What is this straight line equation? It has a slope. We call this slope is the bias, okay, of the slope of this curve. What's the straight line equation now? Is ID of this equation is ID equal to the slope times IR. Okay, so if the current, for the differential current higher than KIR, then it means it's up here, it's up above the blue line when the I differential greater than this. Now if we put AND between the two conditions, I will get this the red area, which is the overlap between the two conditions. Which is now this file. The overlap is this. So this means that this is the trip region. Okay, and now I can also use this equation that when ID greater than I setting plus KIR, which is a straight line equation shifted up by IS. Okay, this is like a slope equation, y equal to mx plus c, right? Math, straight line equation. This c is IS, and the slope is k of this, and k is a setting. Now in a relay you have two settings, a differential relay. It has IS and it has k setting. That's all what I need. And then you compare I differential, which is the difference absolute, with IR, which is another signal I want average of the magnitude of the two currents over 2. Okay. And now if this differential current greater than the straight line means I am above this line, and relay here operate, okay, if it lies in this area, and restrain if it lies below this area. Okay, how do you choose now? Now in manufacturers, like you go to different manufacturers, some manufacturers review a single slope characteristics, some they give you dual slope characteristics. So at the end, what you want to achieve, you want to try to mimic the slope of the error, the error curve as much as possible. Okay, so that we have better sensitivity. Okay. Now, how do you choose these two settings, the slope setting and the pickup setting IS? The slope normally between 10% to 40%, and the 10% normally we take it when you have generator differential, and you go for higher for percentage slope when you deal with transformers. Okay, why not less than 10%? Because the normal error of a CT is sometimes, if I use 5P CT, 5P class, you have already 5% error due to CT. So the primary current with respect to, you have a 5% error. Okay. As a result, I cannot take a slope less than 5%. So you go to 10 now. If we have one relay is plus 5, another relay minus 5, you have already 10% error. Sorry, one CT5 give you an error of plus 5, another give you minus 5%. You have already 10% error due to just the CTs. So CT, the pickup setting shouldn't be less than 10% of the rated secondary current. Now I'm talking about rated secondary 5 ampere or 1 ampere. So take, sorry, no, this is about the slopes. So slope is not less than 10 because of the CT errors at least. So you go to 20% minimum, roughly in practice. And when we talk about generator differential protection, but for transformer we go for 40%. This is what I'm talking about transformers. Now this regarding the slope. What about the pickup settings here? The minimum pickup settings, this settings. Okay, this is taken as depends on, if you have a generator, it will take 5 to 10% of the rated secondary current, which is 5 ampere, rated secondary current of the CT. Rated is 5 ampere or 1 ampere, as I mentioned. So for 5 ampere American standard CTs, we'll take 5% of 5. I'll give you 0.25 is our backup setting for generators. Up to, we can go to 10%. For transformer, we go 20% of I pickup. So I'll get 1 ampere. So I know how do I choose this and how do I choose the slope. Okay. So this is only 2 settings I need. There is no need for coordinations. Okay. So all differential relays need, it needs ID signal and IR signal, which is for numerical relay, it's just computation. No? I take a difference between the 2 currents, I take the average of the 2 currents, then I'll compare, I'll check the equation, if this equation is satisfied or not, this equations, or is it satisfied or not? Okay. I will stop here. Okay, inshallah, in the next class I will try to present the differential, how do you apply differential protection principle on transformer to protect transformer windings. Okay, and I'll also give you an example. Do you have any questions?
Thank you, دكتور.
Okay.
دكتور الكوز بيكون الساعة 7 نفس الكوز الماضي صح؟
الساعة
7 الكوز حيكون. ما أعرف، ما بتكلم عن الجميع، الرد أحد، بس أنا أعرف الكوز الماضي كان الساعة 7.
تبغون 7 بظل 7، أنا ما عندي مشكلة. تبغون 8 بخلي 8 الساعة 8.
دكتور هو المهم الوقت، مش مهم المهم مدة الكوز، مش مهم متى يبدأ. المهم إنه يكون في وقت نحل. يعني دكتور والله الكوز الماضي لولا محاولتين ولا كان صعب. الحين محاولة واحدة، يعني محاولتين المرة الماضية حليت بس 6 أسئلة.
لا تخاف، يعني المحاولتين أو المحاولة بتكون كافية إن الواحد يكمل.
يعني دكتور المحاولة الأولى ما قدرت إلا 6 أسئلة.
محاولة واحدة يحتاج إنه وقت إنه يروح يسأل فلان وعلان، وهاي خلاص يا دوب إنك تطالع حلك يعني. أوكي، أنا المرة اللي فاتت أعطيتكم too long time، يعني أعطيتكم 2 trial within 3 hours.
بس دكتور ترى المحاولة الأولى ما كانت تكفي لحالها.
إيه، عشان كذي إن المحاولة الثانية دائما كان حصلتون فول مارك. أوكي.
بس الأولى دكتور كحل إنك تحل هذا ما تقدر تلحق. اللي
أوكي.
قدرت عليه 7 أسئلة من 10 بس، وخلص الوقت وسلم لحاله.
المحاولة الأولى إيش فيها؟
دكتور كان يعني الأسئلة